canonical means standard, right? So it's some kind of standard. It's a standard ensemble. Like in classical mechanics, the canonical equation of motion are the standard equation of motion. The micro-canonical ensemble was designed for a system that is isolated. It does not exchange heat with the environment. It does not perform work on the environment. It's in a fixed box. But very few examples are like that. Very few systems that we could say that it's a total isolated. Most systems that we know are maintained at a fixed temperature. And then you ask, how do I represent such a system? A system that is not isolated, but maintains a fixed temperature. Say by being in contact with a large body with a fixed temperature. And this is the canonical ensemble. We do not introduce new concepts to do this. All we do is we just take a micro-canonical example of a system and look at a small sub part of it. This is our system. System 1. And this is system 2, which is much bigger than 1. You're just going to have a small part of the system. But this is still very, very big. It still contains an infinite number of particles. But the other system is even bigger. Such that any change, any motion in this system does not affect the big system very much. So this system is called heat reservoir. As we talked about last time, the condition that one part of a system is in equilibrium with the other part in the micro-canonical ensemble is that the two systems have the same temperature. And therefore, this heat reservoir has a certain temperature, and that sets the temperature for the small system. And of course, they exchange energy. So the small system is not micro-canonical because its energy fluctuates. But it's maintained at a fixed temperature by the bigger system. You might conceptually say this. Here's our system. It is not isolated, but it exchanges energy with a much bigger system, which is called a heat reservoir. This is heat reservoir. Which maintains the temperature T. And the heat reservoir is so big that no amount of energy exchange will change its state. And that's the idealized definition of a heat reservoir. And now this whole system can be treated as a micro-canonical ensemble, so we know how to treat it. There are no new principles. What I want to know is what is the phase-space probability for the small system. So let gamma 2 of E2 be the phase-space volume occupied by system 2 in its own gamma space. And of course, both systems are very large. So we say that the total Hamiltonian P1 x1 P2 x2 is equal to H1 of P1 x1 plus H2 of P2 x2. And we neglect any interaction terms across the surface, which means that the surface area is very small compared to the volume. And this means that the total energy is equal to the energy of the first system plus energy of the second system. And in the micro-canonical ensemble, we fix E. And these two can fluctuate because they can exchange energy. And E2 is the energy of the large system, and it fluctuates. So we ask, what is the probability that system 1 is in dp1 dx1 in its own gamma space? And this must be equal to dp dx, the volume element in this time, times whatever the second system does. And whatever the second system is just gamma 2 of E minus E1. Because I don't care what the second system does. So this is probability. And this by definition of dp times dpx times rho of p1 x1. This is the distribution function for the ensemble for system 1. And therefore, the ensemble density for system 1 is rho 1 is equal to p1 x1, and it's equal to gamma 2 of E minus E1 up to a multiplicative constant, up to a factor, up to constant factor, because we have not fixed the units. So this is the phase space density for system 1. However, we have not yet put in the assumption that system 1 is much smaller than system 2. Now we take the limit of the system 2 is infinitely larger. It becomes a heat reservoir. So let S2 of E2, this is the entropy of system 2, be equal to K log gamma 2 of E2. And we need gamma 2 of E minus E1. So K log gamma 2 of E minus E1 is equal to what? E1 is the Hamiltonian of system 1. So this is equal to K. This is just equal to E2 of E minus E1. And E1 is this energy of this first system, E is the total energy. So E1 is much smaller than this. So we expand in a Taylor series about E. So as you get S2 of E minus E1 times D S2 of E prime, say, dE prime is that E prime is equal to E plus higher terms. And those higher terms will be very small if system 2 becomes very large. Now you notice what is this factor here? This factor here is the derivative of the entropy with respect to its energy. And therefore this is equal to this system. It's just equal to 1 over the temperature of system 2. So this is equal to S2 of E minus E1 over KT. And this is the this gives the ensemble So there was a rho 1 of P1 and X1 is equal to e to the S2e over k times e to the minus e1 over kt. And I can drop this because it is only determined up to a constant factor, and that's a constant factor. And therefore I take and also drop label 1. Now we just call P1P, and therefore the density function for a canonical ensemble is rho of P and X is equal to e to the minus e1 of kt. E1 is just Hamiltonian, h of P and X over kt. And this is the canonical ensemble. You notice it's not uniform. The energy comes in an exponential way. And the one parameter that's given is T. It's specified, and T comes from the heat reservoir. The partition function is defined as the Q n particles in a volume V with one T. Given V and T is by definition integral d3n of P d3n of X. We put in a scale factor to make it dimensionless, e to the minus beta h of P and X, and beta is 1 over kt. And the scale tau must be of dimension P3n times X3n. And it must also contain so it's just a scale h. H to the 3n power times n factorial. This n factorial is the correct Boltzmann counting. It just says that the phase space, you only take 1 over n factorial of your phase space. And this h is a number of dimension momentum times distance. It turns out to be Planck's constant. In hindsight. Because when you do this thing in quantum mechanics, when you reduce it to this turns out to be h. And h, of course, is a cell U volume in the phase space. Because the uncertainty principle said that you can only determine P and X up to h. So it's just all reasonable. But at this point, it's just a scale parameter. Later, we'll determine that it's Planck's constant by doing quantum statistics. So this is the partition function. From this, you can get all of thermodynamics. And we also fix it so that it's correct Boltzmann counting and so forth. So how do you get thermodynamics from this? The connection is the assertion that Q, the partition function, is equal to e to the minus beta Helmholtz free energy A of V and T. A is a free energy. You notice for free energy, the natural variables are V and T. And once you have this, you can derive all thermodynamic functions from A of V and T. How do you justify this? By the way, A and T, of course, is equal to U minus Ts from thermodynamics. It's a free energy. U is the internal energy, but that's not always free because you cannot always use it. Part of it is heat motion. The part that you can actually use and do work is this minus Ts, not for the free energy. So let's check this, that this is correct. To check this, you calculate U is equal to the thermal average of H, the Hamiltonian, which is equal to integral dP dx H e to the minus beta H divided by integral dP dx e to the minus beta H. I don't need the tau because it cancels in this case. And this is equal to minus dd beta of the log of Qn. So if I have the partition function, I take the log, I take dd beta, I get the internal energy. So now I check this relation. Just by writing it out. Writing out that relation I have, under integral dP dx divided by tau times e to the minus beta h. That's a partition function. And this is supposed to be equal to e to the minus beta a. So let me rewrite this dP dx tau e to the beta a minus h of px is equal to 1. I bring the a over, I'll write it this way. This is a constant factor, so I can bring it in and out of this integral. Now I take dd beta on both sides. On the left side I get integral dP dx of tau. Let's get a plus beta dA d beta minus h of p and x e to the beta a minus h of p and x. This is equal to 0. Get the differential. So these are just numbers, I can take it out. So I get a plus beta dAd beta times integral e to the beta a minus h here minus e to the beta a integral dP dx tau e to the minus beta h, and the h here is equal to 0. And this whole equation can be rewritten as A plus dA d beta minus U is equal to 0. Is this correct thermodynamically? It is correct because this is, since beta is 1 over kT, this is the same as A minus T dA dt minus U is equal to 0. And in thermodynamics, T dA dt is just minus the entropy. So this whole thing is just A minus Ts minus U is equal to 0. Or the U is equal to, or the A is equal to, this is going to minus S, so A plus, and therefore U, A is equal to U minus Ts, which agrees with the definition from thermodynamics. So that is a correct identification. So now I have this, so now we have two ensembles, microcanonical and canonical, and their relation to thermodynamics can be obtained from different functions. In the microcanonical, you have the entropy as your basic function, and from that you obtain all other thermodynamic functions. In the canonical, you have the free energy as the basic function, and there are others too, so you might know this diagram. This diagram gives you the so-called Maxwell radiations. Each of the, in the center of this A, U, G, and H, they are flanked by the natural variables. A is a function of V and T, U is a function of V and S. And suppose you know A as a function of V and T, then you can find P by taking dA dV is equal to P. But there's an arrow here, so it's minus P. dA dV keeping T constant gives you P. dA dt keeping V constant gives you S, except that you go in the direction, so it's a minus S. So that's the mnemonic. And in the microcanonical, you have to express U as a function of V and S. And then du dV give you minus P, and du ds give you minus T. That is always derivative with respect to one, keeping the other fixed. So this is very useful for doing thermodynamics at a fixed volume at fixed temperature. But in chemistry, you don't fix the volume, you fix the pressure. So this is this function which derives, this is the Gibbs potential. It's a function of G and T, P and T. So as you use P and T as variables of V and T, you keep the pressure fixed. And this is H is the enthalpy. So you have the free energy, the internal energy, the enthalpy, and the Gibbs potential. And given this diagram, given each one of them with the right variable, you can find out all the thermodynamic functions. And those are called the Maxwell relations. And the canonical ensemble is very easy to use. So let's calculate the ideal gas. Then you have Qn of V and T is equal to integral d3n of P d3n of X divided by tau times e to the minus 1 over 2m kt P1 squared plus Pn squared. And this integral, the x integral immediately gives you a factor of v to the n power divided by tau. And then it's times d3p times e to the minus p squared over 2m kt. This is the n power. Or better, it is equal to V over H over N times 1 over N factorial. I have dP from minus infinity plus infinity e to the minus p squared over 2m kt to the 3n power. And this is a Gaussian integral that you can do. And the result can be expressed very neatly in terms of the thermal wavelength, which we introduced a while ago. This integral this can be written this way. 1 over n factorial V over lambda cube to the n power. And lambda is a thermal wavelength. Lambda is 2 pi h bar squared divided by mkt into the square root. This is a thermal wavelength. It's a wavelength of a de Broglie wave at an average energy of kT. Of course, we're doing classical physics, but this enters because we have h, because we identify our h with h bar. So Qn is equal to this. So this is this result. So it's very neat. You don't have to do any counting or anything. You just do the calculation. You do the integral, and you do this. Now, does this give you the correct answer? Let's see. And that's very neat. You see, you have 1 over n, then V over lambda cube is dimensionless, clearly. So let us see if this corresponds to what we know from thermodynamics. Let us calculate the free energy, because Q is supposed to be e to the minus free energy over kT. So this gives you A of V and T is equal to minus kT log of Qn is equal to n kT times log of n lambda cube minus 1, where n is the density, n over V. So it's very nice. It's for the n, and inside is just the density. Where we have used the Stirling approximation. Log n factorial is equal to n log n minus n. Now from this you can get the entropy. Entropy is equal to minus dA dt, keeping V constant. You just differentiate it. You get nk minus 5/2 minus log of n lambda cube. No additive constants. This is absolute, because we put in a scale factor. And this lambda cube involves Planck's constant. It's a scale, but we interpret Planck. If you put in Planck's constant, this is correct experimentally. This is called a Sacca-Tetrode equation. You see, in classical thermodynamics, it was so hard to determine the absolute constant. And when they measured it and found out this is correct, they were very happy. So this is called Sacca-Tetrode equation. And so we just derive it in just was doing integral. There's no counting or anything. And that shows you the convenience in using the canonical ensemble. So the significance of this is this is an absolute entropy. No additive constants. Now we have to analyze the canonical ensemble a little bit more carefully. And we're going to talk about fluctuations in energy. As opposed to the microcanonical ensemble, the energy of the system is not confined to the energy surface in the canonical ensemble. In fact, it is distributed in an exponential way in phase space. So schematically, if this is P and X of phase space, the energy surface might look like something like this. These are different energy surfaces. There's different E's. In the microcanonical ensemble, you choose systems that are uniformly distributed over E. Here, no. Here the distribution is e to the minus e over kt. So it's very dense here. And it thins out exponentially. So you say, oh, the energy fluctuates wildly. No, that's wrong. The energy does not fluctuate. Oh, why is that? Because although the energy is very dense here, the surface of E here is very small. You cannot imagine what happens in an n-body system. If you go a little bit, the surface just expands exponentially. So we have to really calculate the energy fluctuation. Actually, the energy fluctuation does not fluctuate at all. So we calculate the average energy and then calculate the mean square fluctuation. So U is equal to minus dd beta of log Qn, we showed, is equal to minus dd beta and equal to dp dx log of this minus beta h. We can skip the tau because we can put it in. And this is equal to, of course, integral dp dq of h e to the minus beta h divided by integral dp dq e to the minus beta. This is the average of the Hamiltonian. And that's the average energy. And we ask, what is the fluctuation about this energy? That is, if you go from system to system in the ensemble, do their energy deviate very much from U? We will see that the answer is no. They hardly deviate at all. And in the limit of a large number of particles, the energy is fixed. And to do that again, I calculate the mean squared fluctuation in U and use the same trick. I differentiate U again with respect to beta. So I calculate du d beta. This is equal to minus integral dp dq h squared e to the minus beta h divided by dp dq e to the beta h. And then I have to differentiate the denominator there. And it comes to me minus integral dp dq e to the minus beta h squared. And when I differentiate it, I get integral dp dq h e to the minus beta h. But there's already one such factor there. So it's dp dq h e to the minus beta h. So all told, this is equal to minus h squared average plus h average squared, which is the fluctuation. So the fluctuation is just equal to the derivative of du d beta. Let's work out du d beta is equal to, on the other hand, it's going to minus du dt times kt squared, since beta is 1 over kt. And du dt is just the Swiss heat capacity at constant volume. So this is minus kt squared, heat capacity at constant volume of the system, whatever it is. You can measure this experimentally. And therefore we have h squared minus h average squared is equal to kt squared times the heat capacity. Again, this side is all the n squared because it's 10, and CV is all the n, so it's very small. If you divide both sides by CV, you get something that's very small. Again, h squared minus h squared divided by n squared would be equal to kt squared CV divided by n, 1 over n. And this is ortho 1, so this approaches 0 when n approaches infinity. So again, it's a remarkable thing. You consider a subsystem of the microcanonical system and let it exchange energy with the surrounding. But the system, but the average energy is doesn't change very much. The fluctuation is very small if the number of particles is large. But of course, if the number is small, then you don't have it. So again, that is why a canonical example is equivalent to the microcanonical example. You don't fix the energy, it fixes itself. And this is a much better ensemble to work with. In order to emphasize this fact, let us look at this in a slightly different angle. The partition function is integral d3n of p d3n of x by tau times e to the minus beta h depending on p as x. Now h is an energy, but here's a sum of its states. And for given energies, there are many, many states. That's the key. In order to show that, let us just put in, this is equal to, of course, integral dp dx. I just omitted 3n for sure. I would say integral dE of delta function e minus h px e to the minus e px. This, of course, is equal to 1 because when e integral to delta, I get 1. So I'm just inserting something, unity. But then I interchange the order of integration, so I get integral dE. Integral dp dx over tau delta function of e minus h px. And now for that, I can take it out. I can say e minus beta e. This thing is the density of states. So this is equal to integral dE omega e times e to the minus beta e. So if you look at this integrand, now it's an integral over the energy instead of over states. But you have this density of states factor. So now the integrand of this integral, this function e. First there's this e to the minus beta e. that is the density function of the canonical ensemble. You would think that the energy is distributed exponentially, but it's not true because it's an omega. And omega E for a system is goes up extremely fast. When you modify it to, you get a very sharp peak here. So this integral is sharply peaked. It's peaked around what? It's peaked around U, the average energy. And this width is very small. It is a fluctuation. So that this integral actually is an integral over a very extremely sharp peak, centered about the average energy, with the width like the fluctuation, that's a variance, so that when the number of particles is very big, this is a needle. So even though the distribution is exponential, the density of states rises like that, it squeezes it into a peak, and the energy doesn't fluctuate. And it is very, yeah. Okay, I think we should stop here. And you will know that from going to the micro-canonical to the canonical, we relax the condition on energy. Energy will fluctuate, but it fixes itself. Another annoying thing about this still is that we fix the number of particles. Now, we never know the number of particles in a glass of water, for example. So we should let that fluctuate too. And that will be called a grand canonical ensemble, and we'll talk about it next time.